over to you. Apurva, please start from beginning.
Okay. A very pleasant morning to everyone present here. I, Apurva Pathak from Vidyagyan School, welcome everybody to this online summer course. With the collaborative efforts, Shiv Nadar University, Vidyagyan School and Shiv Nadar School have organized a series of webinars scouting the cosmos. Here, through these workshops of online summer course, we bring an outstanding staff of volunteers to illuminate the young minds with the most significant field of study in today's world, space science. We aim to impart the latest and detailed knowledge on space to the students. Today, on the date of 11th June 2022, we initiate our first session on the greatest unsolved mysteries of the universe, which covers the topics such as dark matter, dark energy, and gravitational waves. Kavya and Nishtha of Shiv Nadar School, Noida, are our today's volunteer to furthermore on the session. We hope at the end of the session, attendees would be able to understand the greatest mysteries of universe in detail and have fun-filled quiz, activities, and interactive learning. Yes, here is your chance to seize the day. Ask and learn. Now I hand over the stage to Kavya and Nishtha.
Thank you, Apurva. Hello, everyone. Before we begin with the whole session on the greatest unsolved mysteries of the universe and talk about the nuances of dark matter, dark energy, and the Fermi paradox in general, we would like to quiz you with this. Okay, I'm sorry. We would like to quiz you with this little quiz we created. So I would request all of you to, okay, firstly, let me know if my screen share is visible. Guys, could you let me know if my screen share is visible?
Yes, it's visible.
Okay. I want all of you to go to joinmyquiz.com quickly on your mobile phones or like open a different tab on your laptop and go to joinmyquiz.com. There isn't any spacing in between any of those. And enter the game code, which is 507723. Quickly, and then I could get to see you over here. This is a little bit like Kahoot, except that I had Kahoot free version, so I could not get more than 3 people. So we decided to shift to quizzes. Once again, I'm gonna screen share again with audio this time. Okay, I think this is better. Okay, are we waiting for people or can we begin? Okay, I think we are waiting for people. I'm just gonna keep this open for another 2 minutes. Once again, it's joinmyquiz.com and 507723 is the code. Also, by the way, this quiz is a timed quiz. So like you get a particular amount of time per question. And sometimes it's 30 seconds, sometimes it's 20, sometimes it's even 10 seconds. So I want you to be very mindful. On your devices, you're going to see like the timer thing come down to 0. So I want you to be very mindful of the timer. Okay, are we expecting more people? Wait, I think someone just joined. Okay, are we waiting for more people or should I begin? Are people joining? Okay, I think I'm going to start now. You can join in middle of the quiz too. This quiz is essentially on the greatest unsolved mysteries of the universe. Basically, sort of like a background check of the information you currently know that might be important for the session so that you could enjoy the course content that we'll be discussing a little bit better and you could understand everything a little bit better. So, yep, best of luck. Good luck. I'm starting the quiz right now. Okay, so the first question is that a galaxy is a huge collection of stars, dust, and gas in their solar system. What holds a galaxy together? You get the options on your screen, so you just have to tap. Guys, also this is time, so you need to make sure that you sit on time. Okay, so a lot of people did black hole and dark matter and the sun. The sun keeps our solar system in order. The sun does not keep our galaxy in order. And ultimately, it's gravity. Everything that has mass is gravity. So it's gravity that holds us, holds the galaxy in order. Okay, why did Einstein win a Nobel Prize? We have 5 seconds. We have Vidush on top with 10 points. Oh, wait, okay. A lot of people usually think that Einstein won the Nobel Prize because of theory of relativity, but people actually were very against the theory of relativity at first. So they actually used to debate a lot about the nature of relativity, and 100 scientists came together to oppose the theory of relativity, and Einstein actually said that if I was wrong, one would have been enough. But Einstein actually won the Nobel Prize for photoelectric effect, which proves that light can exist both as a particle and as a wave. Okay, I think this one was a little tricky. 12 people have actually walked the moon on a lot of different Apollo missions.
Ma'am, isn't the first person to walk on the moon Neil Armstrong?
Yep. The first person to walk on the moon was Neil Armstrong. But this one's a little tricky. So when you're playing with your friends and you hold hands and spin together and the thing that we're talking about right now, and you feel an outward force. What is that force called? Okay, we have Vidush holding first position again. The force is actually called centrifugal force, which is what happens when one thing keeps on spinning at its spot over and over again, which is exactly what happens when you take your iCard and you spin it around. So the iCard also feels an outward force, and that is centrifugal force. Okay, can light ever be bent? So the answer is yes, light can be bent. And light can be bent in two main ways. One is refraction, in which light changes mediums. And so it bends because of a change in the density of two mediums. And another way light bends is something we'll be exploring right now, which is called gravitational lensing. When gravity bends space-time, and space-time is the path that light takes, so light also bends. Okay, our second last question. What is the name of this high energy particle accelerator? Okay, we have Apurva on the first spot right now, and the answer to this was the Large Hadron Collider. Laser Interferometer Gravitational Wave Observatory is something called LIGO, which helps measure gravitational waves when it passes through our planet. Massive Astronomical Compact Halo Object is one of the candidate particles for dark matter, which is something we'll be talking about. Okay, last question. Yep, last question. Okay, but I think we had too less time. But okay, so quiz is over. Now we're going to see the results. On third position, we have Ani, if that's how you pronounce it. Second position is Daksh. And first position is Apurva. Okay, so I hope you could get something out of this quiz. And congratulations to Apurva. Thank you so much for playing the quiz. And now we'll be moving on to the presentation, which is on the greatest unsolved mysteries of the universe. Give me 1 second to figure out my presentation. Okay. Yep, I think, okay. So greatest unsolved mysteries of the universe, it is being presented by Nishtha and I. Nishtha, can you say hello to everybody?
Hi everyone, I'm Nishtha from Shiv Nadar School, Noida.
Yep, I am Kavya from Shiv Nadar School, Noida. I'm in grade 12 international curriculum, and Nishtha is in, Nishtha, come on.
CBSE.
Yep, Nishtha is grade 10 CBSE. Okay, so dark matter, dark energy, and Fermi paradox. Out of these, I'll be covering dark matter and the Fermi paradox, and Nishtha will help you out with dark energy. Because frankly speaking, I don't understand a lot of dark energy myself, so Nishtha is the person I go to. Okay. So, the universe. Out of everything, which was, I think, the last question of our quiz, which was that out of everything in the universe, okay, so all the planets, all the light energy, all the dust, all the stars and huge like galaxy clusters, Milky Ways, everything. Okay, everything we know comprises only 5% of the total mass and total energy of the universe. Everything we know. So like this table that I'm sitting on currently, and like essentially everything around you. And wait, is my voice clear? Can you hear me properly? Nisha, can you hear me properly?
Yeah, it's clear.
Okay. Sorry, I think we'll have to work on the internet or something. All right. So everything we know, everything scientists have been studying for like centuries is only 5%. And 5 times of what we know right now is something called dark matter. And 70% of the universe almost is something called dark energy. And so what is this dark matter and what is this dark energy that comprises such a huge part of the universe that most of us don't even know about? So I'll be talking, like I said, about dark matter, and Nishtha will be talking about dark energy. So firstly, we'll be talking about dark matter. Does anyone have any idea what dark matter is? Before we begin, I can't see if people are here on Zoom. Nishta, can you let me know if there are responses?
Yeah, sure.
Okay, even if you do not, I think we'll be going step by step on how dark matter discovery essentially started from 1920s. Wait, guys, can you please? Okay, yeah, very black and dark matter. Yes, okay, true. Dark matter essentially was called dark matter because people thought they could not see it because it did not interact with light. But I think it'll be more convenient if you just think of it as, I don't know, like invisible matter, because we cannot see it, it does not interact with anything, and we just know that it has mass. So maybe invisible matter would have been a better term to go with. But dark matter actually started as a joke to say that, oh, wait, you don't understand the universe. Oh, wait, what does it have dark matter in it? And so people started mocking physicists who used to believe in something called dark matter, which is also the story for Big Bang. Because people said, oh, wait, you think the universe started with a huge boom? Oh, what do you call it? The Big Bang. And the name kind of just like stuck around, which is the story for dark matter and dark energy. Okay, so dark matter was a term that was first proposed in 1920s, but it was only taken seriously in the 1960s. And now we'll be talking about 4 reasons why we know that dark matter actually exists. Okay, let us say you have this galaxy and you need to measure the mass of this galaxy. You're a scientist, okay, and your job is to measure the mass of this galaxy. Now, okay, you sit down one fine day and then you're like, okay, let me measure every planet there is, every solar system there is, every star there is in this entire galaxy, and measure it from like top to bottom, measure everything, account for everything. And so, okay, you start doing that, and when you calculate, your calculations show that it is 200 billion. Okay, can somebody tell me what the unit is? Nishta, can you tell me what the unit is?
Solar mass.
Yep. You measure astronomical objects in a unit called solar mass, which is denoted by this M, and I don't even know, concentric circle thing that you can see over there. So let us say that you measured and you added everything up, and it said that this galaxy weighs 200 billion solar masses, which means that it is 200 billion times the size of our sun. Okay. And you accounted for everything. But then you actually, let's say you took a weighing scale and you decided to weigh the galaxy. And the result of the weighing scale was 1200 billion solar masses. Now, this difference is huge. Okay? This difference is too big for it to be just a calculation error. And how, okay, let's be real for a second. Okay, scientists don't actually have a weighing scale to measure masses of galaxies. How do scientists find out if their calculations by individually adding up every solar system, every little galaxy, chunks in this huge galaxy cluster make sense? They look at other factors like what is the gravity of this galaxy, by how much does it bend light, and they look at all of these different factors, and you see this discrepancy. You see that from 200 billion solar masses, it is at 1200 billion solar masses. So this difference cannot just be a mathematical error. That means that there is something that we are not accounting for, and something that is missing in this entire. Okay, I know this can sound a little bit complicated, so I'm just going to give an easier example. Okay, let's see you're standing on a weighing machine, and you know for a fact that you weigh 50 kg. But when you stand on the weighing machine, it tells you that you weigh 60 kg. Okay, so the difference is huge. 10 kg is huge difference, and you want to make sure, you want to know why that happened. So there could be 2 reasons. One, either there is somebody adding mass or something adding mass and you cannot see it, and you just know that it's there based on interactions and everything, and either like that is happening, like invisible force acting mass or everything, or your scale is broken, which is what is the exact reason that scientists use. So if the mass of the universe does not add up, either there is something called dark matter which is acting over here, or all our laws of physics, everything that we took build like thousands of years to make right now, is completely a scam. Is everything is incorrect. So that was what was supposed to be the whole premise of dark matter. Now there are a lot of other different theories that come at play over here, but dark matter also was called dark matter because it keeps our rules of physics in the dark. Now we'll be looking at another proof, which is the spinning of galaxies. Wait, I got this very cool animation which seems to not work right now, so that was sad. But oh yeah, it worked. Okay. Galaxies spin. Why do galaxies spin? Nisha, would you like to help me out here? Why do galaxies spin?
Because of gravity.
Yep, galaxies do spin because of gravity, but how? Why? You know, a lot of things in this universe just happen because of gravity. So if a random person asks you a question, just say gravity. I'm pretty sure it's going to be correct. But why exactly, because of gravity, do galaxies spin? Okay, yeah, Daksh, go ahead.
I believe because in our galaxy, let me take the example of Milky Way. I'm not sure, but I'm pretty sure that there's a black hole in the middle of the Milky Way. So, maybe the black hole, which is also producing gravity, maybe it's also pulling in the other gases and dust in our galaxy. That's why it's making it spin.
Although that I see why that makes sense. Oh, Daksh, do you know the name of the black hole at the middle of our galaxy?
I'm kind of forgetting.
It's called Sagittarius A, and it's hitting the news right now because recently scientists were able to, like scientists at Event Horizon were able to take a picture of that black hole.
That happened in, I believe, 2020 or 2021. They won a prize for that.
Oh yeah, that was M814, which was another black hole, but they just pictured Sagittarius A like 2 weeks ago, which was very cool. I think you should look at the picture for that. Shaurya, could you unmute and say it out loud instead of writing it to me on chat?
Yes, ma'am. Maybe it is something related to centrifugal force to like keep something in balance so that everything doesn't, just move apart.
Yep. So that is correct. Even though black hole, like Daksh said, makes a lot of sense, but the thing is, not a lot of galaxies have black holes in the center of them, and they still spin. So even though scientists used to believe that initially it was because of black holes, so that is where you're correct. Recent theories like show proof for the fact that it is actually because of centrifugal force, which means that because stars and everything has so much mass, a galaxy would collapse into itself because of gravity. But even if there is a black hole at the center of a galaxy, it does not like collapse into it. And that happens because of centrifugal force that is generated from this spinning. But okay, that is all good and done. But why are we talking about dark matter and centrifugal force all of a sudden? Well, so the thing is, galaxies actually spin at a rate faster than what they're supposed to. Okay, so let us say that, you know, that example of you holding hands with a friend. Let's think about that again. I'm sorry, this is the best video I could find to demonstrate. Okay, let us say you and a friend are holding hands and you're spinning. Okay, it is all good and you're spinning casually and everything is going properly. Now imagine you're spinning, but you're spinning like super fast. Okay, and if you're spinning super fast, there's a huge probability that you're going to fall. Obviously, and that is the exact same thing that is applicable for galaxy. If a galaxy is spinning very fast, there is a huge probability that stars would just like shoot out because of, again, like Shaurya mentioned, centrifugal force. So why does that not happen? We don't see stars like shooting around and hitting us all the time. Why does that not happen? That does not happen because there is this tape that sticks the galaxy together, and this tape is what is dark matter. Okay, this is the simplest analogy that I could come up with. I'm sorry. But basically, dark matter are like blobs of mass that are just present in the galaxy. And this blobs of mass, okay, something that has mass has gravity. So this blobs of mass is what pulls the stars together and allows for galaxies to spin at the rate that they are actually spinning. Okay, now remember I asked, okay, this is again talking about why this allows for the galaxies to spin. Okay, again, does anybody remember the answer to the question of why light could be bent or not? Yes, can light be bent? Yep, Nishtha.
There are two ways. like you
Okay,
talked.
what are the two ways?
So one is refraction, where light is bent because it's passing through like mediums of different density, and the other one is gravitational lensing, which I think you're going to talk about.
Yeah, gravitational lensing is something I would be talking about. Um, yeah, so like Nishtha said, the number one way, why is my slide not changing? This is so sad. One second. Yeah, like Nishtha said, first way that we know light can bend is because of refraction. And this is a very common illusion. I think you're going to study in grade 7. I'm not really sure about the curriculum. But you see how apparent depth and perceived depth is two different things that happens because of an illusion that is created because of refraction. And so basically refraction, something like refraction happens on a much grand astronomical scale in this thing called gravitational lensing, in which something that has gravity, like Einstein said, some gravity is nothing but warps and curves in the space-time. And anything that has gravity warps space-time. And so like if I walk on a road and you make the road to go like upper niche and all of the things, so I would also go along with the path of the road because I'm walking on the road. So similarly, this happens with stars. You warp, this happens with light. So you warp space-time and stars, the light warps along with it. So you see a difference in the actual star and a observed star in our night sky. Now this happens on a very grand level with lensing gravity. So there's a source gravity over here, if you can see, and there's a lensing gravity. What does the lensing gravity do? The lensing gravity bends light. So light comes from the source galaxy. It comes in this direction. It should ideally go straight, but the lensing gravity makes it bend and reach to our eyes over there. And so you picture a different ring type of structure and everything. Okay, that is all good and done, but where does that come in terms of dark matter? Well, number one is that scientists have recorded data, like I mentioned earlier, how they used to look at the bending of light and they used to see, oh, look, this galaxy is actually heavier than what it was supposed to be based on normal calculations. This is what happens when they measure dark matter when it comes to gravitational lensing. They say that, oh, look, if this gravity was supposed to weigh, let's say, like 200 kgs, why is it bending light like a galaxy that is weighing 500 kgs? What is that extra 300 kgs? And that is where dark matter comes in. Another way we know that dark matter is responsible for gravitational lensing is that even when there is no lensing gravity in the center, light bends. And we think that light is bending because of this invisible thing that has mass called dark matter. So what do we know about dark matter right now? Daksh, could you help us summarize what we know about dark matter right now?
Well, what we know about dark matter is very much limited.
Okay.
So we know that we know that dark matter is obviously present throughout the universe, and it is also and it can also cause this type of this bending of light to not give us the exact location, except give it like this bending of light can also be caused by the dark matter. I'm not extremely sure about the other parts of the information because I haven't read about dark matter much.
Yeah, I think what you've said is perfectly fine. What we know about dark matter right now is that it has gravity, right? And if something has mass, it has gravity. So we know that dark matter has mass. We don't really know where dark matter looks like or what dark matter is made of or like anything right now, but we know that it has mass. We know that it does not interact with our light because it is dark matter. We cannot see it. We cannot record it. We know that it is present everywhere around us. So these are the things that we know about dark matter right now. Okay. Guys, okay, this is something which is very cool and I was very fascinated when I first saw it. Do you know what the Hubble telescope is? You guys know what the Hubble telescope is? sort of know. Okay.
Yes.
Quick question. Do you know which telescope went there to almost replace the Hubble telescope? What is the name of the new telescope?
James Webb Telescope.
Yep. So the James Webb telescope was launched by NASA. James Webb was supposed to be sent into orbit 4 years ago, but then this is how it works in the aerospace industry. It's usually always very late. And basically, this is the Hubble telescope. It recorded the collision of two galaxies with a different set of pictures, and so it clubbed them together to make a simulation. If you had to see the collisions of galaxies in real life, it'll take millions of years. But since we are so far away, light takes billions of years to come to us. We were able to record this collision of galaxies through a series of different pictures. And okay, what do you observe when these two galaxies collide? You see that dust particles are falling everywhere. You see that stars are crashing into each other. You see a lot of like collisions of matter, and you see ice spreading everywhere. Scientists recorded all of this, and it's like, okay, this happens, this happens, this happens. But what does not happen? The dark matter of one galaxy and the dark matter of another galaxy just pass right through each other. They do not crash into each other. They do not interfere with each other. They do not add up or anything. They just pass right through each other. So we know one more thing about dark matter is that we know that it does not interact with other matter, because dark matter could be passing right through us right now and we would have absolutely no idea. We know that it does not interact with light, and we know that it actually also does not interact with other dark matter. So now we know 3 things about dark matter. Okay, does somebody here know the 4 types of different interactions of objects, which is something people usually learn in like 9th or 10th grade, so I don't expect a lot of people to know about it right now. But there are 4 ways in which things interact with each other. And that is number 1, gravity. We talked about gravity. Gravity, everything that has mass is attracted to every other thing that has mass, which is gravity, and gravity is dependent upon the mass of an object. Then there is electromagnetism, which is positive charge, negative charge, and like light charges repel and like charges attract. Then there is weak force, weak nuclear force, which is responsible for particle decay. And then there's strong nuclear force, which, in the atoms have what? Neutrons and protons. And protons are stuck so close to each other, and protons are 2 positive charges. So they should ideally repel, but they do not repel, which is because of strong nuclear forces. Okay. So these are the 4 forces. And okay, what do you think dark matter interacts with? And out of all of these forces, which force does dark matter interact?
Weak force.
See, I know where you would think that it is weak force. And Shara, can you please unmute and answer?
Electromagnetic force, because like at the center of all the smallest part, the atoms and molecules, there's only one force that is actually variable, that is electromagnetic force.
Yep, I see why you would think that. But see, the thing is, it is neither of those. It is not weak force or electromagnetism, because we don't. Okay, Ashloka, go ahead.
Yeah, I think it will be gravity, because it says if you have any mass at all. So you said that dark matter are blobs of mass that have gravity, and hence I think it should be gravity.
Yeah, dark matter interacts with only one of these forces, which is gravity. Dark matter does not interact with electromagnetism, because electromagnetism is also what? Electricity and magnetism, which is light. Dark matter does not interact with electromagnetic radiation or interact with light or any electric or magnetic radiation individually. Also, because dark matter is not made up of individual particles, we actually have no idea what dark matter is made up of. And so we cannot say for sure if it actually does interact with electromagnetism. And since we do not know if it actually has particles, weak force and strong force are eliminated. So dark matter is actually not as convenient to study as we think it should be, because it only interacts with gravity. Okay, air around you is invisible technically. You cannot see air around you, but you know that you have air around you because you can feel it, and you can indirectly make sense that there is something around you. which is the same thing with dark matter. You can see how it interacts with gravity and you can make sense of the fact that it is there. But it does not interact with anything else, which makes it so inconvenient to measure because the current apparatus that scientists have right now restricts our recording of data to very few forces. So scientists wanted to study what dark matter is made up of. So if you want to study what something is made up of, you usually look at if you want to study something, you usually look at what it is made up of. If I'm a doctor and if I want to study the human body, I cannot study the human body without knowing what bones are or muscles are or diving deep into organ systems and tissues and everything. So if I need to study dark matter, I need to be able to study its particles. And over time, scientists came up with two main theories of what dark matter is made up of. Now it is very much possible. We can't just say that, okay, see, this is Earth. Earth is made up of rock. That would be wrong because we, like humans, are made up of we're carbon-based organisms. There are other things which are, I don't know, like we have plants and we have computers and we have a lot of different things that are not rock. So dark matter could have a lot of different particles in it as well. It could have dark biology, dark chemistry, and a lot of other stuff happening. But for simplicity, we just assume like one type of particles that make dark matter right now. And so there were two main theories. I swear I am not making this up. Scientists said that the first thing that makes dark matter is something called macho. And this is a picture of El Macho, who is my favorite villain from Despicable Me Too. And Macho is massive astronomical compact halo object, which I know is a very long name. And it looks like you forced this name to make it fit into Macho as an acronym. But basically, people used to think that, like Shloka pointed out, vast blobs of almost like Jupiter-like planets that are randomly floating around is what makes dark matter. Now, a lot of research happened and people found nothing like that. So Macho as a theory was initially dismissed. And now people come up with a theory that is called WIMP, which stands for weakly interacting massive particles. Why weakly interacting? Because it does not interact with anything. It interacts so weakly with light, with other objects, with each other that we cannot see its interactions at all. And also, guys, massive is not something that is physically larger in size when it comes to physics. Massive is something that has mass. And when something has mass, it has gravity. So just be sure to make that distinction. And there's a picture of Wimpy Kid to help you remember that it is Wim. So what we know about dark matter, to sum up right now, is that it has mass. And out of the four fundamental ways that we know things interact, the only one that we know for sure that applies to dark matter is gravity, because we've seen it. It does not interact with light or matter, other matter, or even other dark matter. And we think that it is made up of weakly interacting massive particles. Okay. So we know about dark matter. We know all of these things about dark matter. Now, how do we go ahead with research on dark matter? This is where, the Large Hadron Collider, LHC, comes in, which was one of the questions in the quiz. And basically, scientists think that if dark matter collides with another dark matter, it creates particles. So if a particle collides with another particle, it should create dark matter. So this is a particle accelerator. Basically, they squash like particles at very high speed together in the Large Hadron Collider. And that is where scientists expect to find dark matter. Thank you. This was for dark matter. And I would quickly help you go through dark energy. Over to Nishtha.
Thank you, Kavi. Okay, I'm not able to screen share. Okay, it's disabled. The screen share is disabled.
Check now.
I think, yeah.
Yep, it's working. Thank you. Hope my screen's visible.
Yeah, we can see it.
Cool. Sorry. So imagine you're standing on the shore, looking towards the horizon, wondering how far it goes, and if it has always been like this. A similar thought crosses an astronomer's mind when they look up at the sky and try to unravel the mysteries of the universe. For a long time, scientists have wondered if a universe has a beginning or has it existed in its present form forever. As recently as a century ago, on measuring light from our surrounding stars and galaxies, they concluded that everything was moving apart from everything else. The universe wasn't just standing still, it was expanding. And if it was growing bigger, then it must have been really tiny at some point of time. This thought gave rise to the theory of Big Bang, an event 13.8 billion years ago, where a tiny dense fireball exploded to create space and time. When astronomers figured this out, they wanted to know how fast the universe was expanding. Were the other galaxies moving away from us slowly than they were a billion years ago? Or were they moving apart quickly than they used to? They wanted to know how the rate of expansion was changing over time. To know this, they used a very interesting methodology known as Doppler's shift, according to which light from distant galaxies have a longer wavelength and are represented by the red side of the visible spectrum, whereas light from near galaxies have a shorter wavelength and are represented by the blue side on the visible spectrum. So if we know the length of the wavelength, we can figure out how far the galaxy is and how fast it's moving. On measuring light from different galaxies, now the scientists could tell how far away the object were and figure out how fast they were moving. They measured galaxies and calculated the rate at which the universe was expanding, and was surprised to know that it was expanding at a quicker rate than it was actually supposed to. And what was this mysterious force which was accelerating the expansion of the galaxy? The answer to this would be dark energy, which makes an estimated 68% of our universe. And we don't really know much about it. All we know is that it's not visible. We haven't been able to detect or interact with it yet, and it does not have any electromagnetic properties. So we're basically in complete dark about dark energy. And essentially, it's an empty space or a vacuum energy, which is driving the universe further apart. And yep, that's all we know.
So before we go, we would also, Nisha, did you stop, please?
Yeah.
Yep. Before we leave, we would also like to talk about this really cool thing, which is something that we would like to let you ponder upon, and it is something called the Fermi paradox. And 1 second, I'll just let you know like 2 minutes of it so that you have an idea. And yeah, that's it. Basically, there are 200 billion stars in our galaxy, which is the Milky Way. There are 200 billion stars in Milky Way. That is a number so huge that we cannot physically comprehend or compare it to anything right now. And out of the 200 billion stars in the Milky Way, 20 billion are like the sun. Okay. And out of the 20 billion that are like the sun, scientists estimate that there may be 11 billion planets orbiting sun-like stars. So if you associate that with the universe, and the universe has like 200 billion times the galaxies that we are assuming. So there are like 200 billion galaxies in the universe. And our Milky Way has 200 billion stars. That has 20 billion stars that are like the sun, with 11 billion planets that are like the Earth. That is a huge number. And the point should be very clear that there are a lot of Earth-like planets in the universe. So we aren't actually as unique as you think that we are. And even when you take the most conservative of measures, statistically speaking, the universe should currently be flooding with light. Because if there are billions of planets that have that have life in them, where is all of the life? Okay, so given the incredible amount of solar systems that are much older than our own, and many of the life forms in those solar systems, in those planets, would have billions of more years to evolve. And intelligent life in our planet is a couple thousand years old. So we cannot even fathom the technology, the expertise that these new alien species would have. But if this is the case, okay, if the universe is so incomprehensibly vast and it is so richly populated with intelligent life, there is one main question, which is where is everybody? Okay, where are the aliens? And this is something that was proposed by Fermi, who is a physicist who actually won the Nobel Prize for his work on particle acceleration and everything. And this was actually something that Fermi came up with on a lunch table conversation. And sadly, this could go nothing further than a lunch table conversation. But Fermi's friends, after Fermi's death, spread it to media, and this was commonly known as the Fermi paradox, which states that statistically, we should have had contact with aliens. Then why don't we have contact with aliens? So this is something that we let you to speculate right now. So are there any guesses? Why do you think aliens have not made contact with us? This seems like such a science fiction thing to talk about, but this actually makes a lot of sense in domains such as astrobiology. So what do you think, guys? Why do you think aliens have not made contact with us? You said you have any theories on why aliens have not made contact?
Maybe they've discovered us. We haven't discovered any aliens so far, but maybe they know that we exist. But
yeah, maybe they just think we aren't worth their time.
Maybe
they come to us and visit us. Yep. So scientists actually came up with like 3 basic conclusions, which were that 1, we are the only form of advanced life, and none other life has the technology that we have. 2, extraterrestrial life does exist, but has not visited us for some reason. And 3, extraterrestrial life has visited us, but we have no proof that they have visited us. Yes, Shloka.
Maybe they exist in a form that isn't exactly identifiable by us, that we can't identify it.
Yep, that makes sense. See, that's the cool thing, because we can speculate so much about the Fermi paradox, and we have no way of confirming a lot of that.
Yeah, like we don't know like what dark energy, dark matter is made up of, right?
Yep, I hope this session helped you understand how little we know of the universe and how much more we actually need to know. And before we go, we would also like to acknowledge this very pretty book called We Have No Idea, which is my personal favorite. I have it right now with me over here. Nishna, do you have your copy?
It's on the side table.
Can you go get it?
Yeah.
Yep. So I asked Nishtha to read this book, and then all of us just keep on talking about how good of a book this is, and a lot of the illustrations.
It's one of the best books that I've ever read.
Yep, and a lot of the illustrations that we had in this PPV right now were inspired from this book. And it's a very basic level book, and it talks about how little we know about the universe and a lot of different questions. So these were only like 2 aspects, dark matter, dark energy, only 2 aspects of this entire discussion. And there are so many more that this book talks about. So I think all of you should give it a try. You won't regret it, and then you will come to me and thank me, and I'm waiting for that time. Okay, that's it. Thank you. Over to Rachna ma'am, if Rachna ma'am's here.
Oh,
yeah, sorry, over to her.
yeah. So thank you, Nishtha and Kavya, for conducting such an outstanding session on the greatest mysteries of the universe. We praise your uphill efforts I hope all of us had an amazing experience learning with our wonderful tutors. The quiz and the explanation made topic interesting and very simple to understand. We want you all to explore more on the topic and come up with new theories and ideas about the space, because future is going to feed on your minds. Our next topic for next Saturday is exoplanets. Just to give you all an overview, it's about the planets which are outside our solar system. Under this topic, we would cover Alpha Centauri, which is a group of 3 stars nearest to our sun with some exoplanets. We will also cover Goldilocks zone. It is a habitable zone around a star where we expect to find a planet thriving with life. Now, I would like to thank Ma'am Vinita Sharat for being with us, and our mentors, Gulfam sir and Rachna ma'am, for guiding us throughout the webinar. My heartiest thanks to all the participants for attending this session. Thank you, everyone.
Thank you, everyone. We are open to any questions if you have. And I would also like to send my email ID on chat.
Kavya and Nishtha, great job, beta. Wonderful. And in fact, the children who are there, if anybody wants to share some reflections, this is the first episode of the series, if we can call it that. So if anybody has any reflections, any suggestions, you're
If you
most
want
welcome to share.
any concept that you really like and you want it to be covered, I think we can also consider that and maybe see if we could accommodate it in this. Like anything related to astrophysics that you're interested in and you would like to know more about. You can write that on chat or suggest a few.
Okay. Yep. I think. Rachna ma'am, is it possible for us to send along a feedback form?
Definitely, definitely.
I think, yep, that would be helpful. And we request everyone to please fill the feedback form once it is shared. Yes, Shloka.
It's already requested to Naman. First of all, before you share the feedback form, would like to really congratulate Kavya and all the speaker, Nishtha, and I believe it is, Purva. Great session. I like all the PowerPoint. I like everything. Actually, I liked everything. It was really nice. And, the way you made it simple. That is, even I don't know, we as a teacher would have done such a great job. So congratulations. Sky is the limit. Go explore universe. Get engaged the students in exploring universe. Go and join college next year. And you guys are just awesome. Very fit for teacher assistant when you go to college. All the best. May I request Naman to just after a minute to stop live streaming. Before that, I would like Gulfam sir and Rachna ma'am to speak about the children work. Over to you, Gulfam sir and Rachna ma'am.
Yeah, I guess I've already basically these children have worked very hard, and like ma'am said, heartiest congratulations to you. And I hope the other children who are a part of the audience today, you get inspired and not only to research more, but you have to take this legacy forward. The summer programs that we are having over here, as you know, there are 5 programs that would be going on this summers. Children, you are this time it's Kavya and Nishtha. Kavya will be passing out from school next year, so we want you to step into their shoes, learn, and learn not only the new aspects and concepts that we are talking of in these sessions, but also learn how to take the legacy of our school forward. We have to take it to on a much bigger platform. We have to talk about this to our friends, to our families. Like, this is wonderful work which is being done by you children. So I just hope we can take the entire the sessions which have been spearheaded by Vinita ma'am. Vinita ma'am's without her vision and support, this wouldn't be possible. And we hope we can take it to even bigger platforms and more people can join this journey, the better it will be. Thank you. Kulpam sir, all yours.
Yeah, ma'am. Really, it's a wonderful effort they have done. They have put in. Actually, the time they have given to prepare the PPT and finding the examples which are very realistic. So we could not imagine. So I would like to say one thing that everyone should come and congratulate the Kavya and the Nista for this wonderful work. Thank you, everyone.
Naman, could you please stop live streaming, and participants and teachers, please stay for 2 minutes.